So we cannot diagonalize using the eigenvalues. We cannot diagonalize a non-square matrix using the eigenvalues. Okay. We like to diagonalize a lot. I mean, this is something that this is our objective. But if it is n by n, we can use eigenvalue equation. And not only that, we need the eigenvalues and the eigenvectors to diagonalize it. But the moment that A is n by n, eigenvalues can't.
If it is n by n, we cannot find its inverse?
If it is n by n?
If it is not a square matrix, we cannot find its inverse.
That is true, yes.
And so this implies that we cannot
diagonalize it.
We cannot use the formula of diagonalization because it is P inverse.
Well, this is not the only reason.
I think that
it is true that if for non-square matrix we cannot find the inverse. That's one argument. But rather than being a cause and effect, they are both associated. So if it is a non-square matrix, we can simply not diagonalize it using the eigenvalues, because the eigenvalues are defined only for square matrices. Okay, so you can say this that
or I think that the eigenvectors should be linearly independent, so that we can diagonalize the matrix. The matrix in square, I mean.
Say it again.
I mean, you said several reasons. I'm saying that to diagonalize the matrix, we should accomplish the condition that the eigenvectors should be linearly independent, I think, for the matrix if it is square.
Yes, that is true. And all eigenvectors, in fact, they are linearly independent. But regarding the issue of non-square matrices, which we want to diagonalize, or in a different way, we want to say that we want to simplify it, or we want to pick up the best basis, those matrices, we are going to use another trick. Okay, we are going to use indirectly. We are going to use what we learned from eigenvalues. We are going to use those tricks on non-square matrices by multiplying a square which is n by n with its transpose. Okay, but then this topic we are going to discuss it later. So you should know for now that the eigenvalue diagonalization it is possible only for square matrices.
Professor, another question, please. We implied that the number of eigenvalues corresponded to the number of roots. What if we have a polynomial equation that is of the degree 3, and we have, or to the second degree, and we have a double root?
You said the number of eigenvalues, it is related to the order of the polynomial, right?
Yes, and the number of roots. Now, how about in the case that the polynomial has a double root?
If it has a double root, we have to look for the number of eigenvectors. This is what we should look for, okay? But this discussion we're going to make this argument a little later. So if you wait a little, we'll come to that point, okay? So this is what you said. You said the number of eigenvalues is going to be related to the polynomial. This is one option. Or it can be the number of eigenvalues can be m smaller than n, where n is the order of the polynomial. Because you are right, sometimes we might get a polynomial that can look like this. We can have a P3 in lambda, a polynomial third degree in lambda, which can be 3 lambda minus 2 squared, lambda minus 1, this is equal to 0. So it's true. We don't have 3 distinct eigenvalues in this case. So what could happen with the number of eigenvectors, or is the matrix even diagonalizable at all? But we'll come to this point. Before coming to this topic, we want to discuss initially the concept of eigenspaces. Now, eigenspace, it's a set which is composed of the solutions x which correspond to the null space of A minus lambda I. Okay, so eigenspaces, it's composed of, let me write it like this, composed of X such that X is in the null space of A minus lambda I. Now, what is important to notice here is that for each lambda, we have an eigenspace, okay? Because this matrix here, this is going to be different. Okay, so if we have a matrix A, and A has two eigenvalues, such in the previous example, we said lambda 1, assume it's 2, and lambda 2 is equal to 8. Then what happens is that we have an eigenspace which corresponds to this eigenvalue. Okay? Why? Because this would be A minus, since lambda is equal to 2, minus 2i, minus 2 times the identity matrix, and the eigenvectors, they will come up from from the null space of this matrix. Or, for the other eigenvalue, we would have A minus 8i, and then we'll have to look for the null space of this with respect to the other. Okay, so we can say that eigenvectors corresponding to one lambda form an eigenspace. Eigenvectors corresponding to lambda I. So I want to denote this one lambda I because each lambda has its own eigenspace, constitute or form an eigenspace. And now it is worth mentioning a couple of interesting properties of the eigenvalues because we are dealing with eigenvalues and eigenvectors. One of them is that this is like a rule, the determinant of a matrix A, this is equal to the product of lambda I, okay? And the trace of a matrix A, this is equal to the summation of the lambda I. So this is equal to lambda 1, lambda 2, lambda n, and this is equal to lambda 1 plus lambda 2 plus lambda n. So these are some important relations. Another thing is that we have another definition, which is worth putting it together in the formal way, which is the following. So we have the definition here, which states that A is diagonalizable if it is similar to a diagonal matrix D. Okay, so this is a formal definition which states that A, it can be diagonalizable if it is similar, but being similar to a diagonal matrix D, this means that D can be written as P inverse times A times P. So in order to have this possibility, then we should be able to find a matrix P which is invertible, and these two satisfy this condition. Okay. So this is another extra definition regarding the diagonalizability of a specific matrix. Now, another theorem that we can put here, so this is something which leads to our intuition of how we can think about the matrices and diagonalizability. Here, we can provide another theorem which is as follows. A n by n is diagonalizable A n by n, which means that the square matrix is diagonalizable if A has n eigenvectors. So it looks like having n eigenvectors is a very tough constraint. Okay, so it should be, we should have those, and then Okay. Then we can talk about the geometrical interpretation. Another statement that we can put forth is that so here we can put another theorem, which is the following. Any two distinct eigenvalues or any two different eigenvalues from each other, they have different or they have linearly independent eigenvectors. Have linearly independent eigenvectors. Okay, so this is also very important. And regarding this means we can report the following. So let's assume we have a matrix n by n, and then if we have n different eigenvalues, but different from each other, is this matrix A diagonalizable? What do you think?
Since
Yes.
we have different eigenvalues, we will have linearly independent eigenvectors, so it will be diagonalizable.
That is true. So if you have n different eigenvalues, then this means that immediately we have n
Eigenvectors, linearly independent eigenvectors.
eigenvectors. Yes, that's true. And then this means that a n by n would be diagonalizable. So let's pick up an example here. So here we have a matrix which is -3, 1, 1, -1, -1, 1, -2, 1, 0. So here we have a matrix. It is 3 by 3, and we want to extract as much information as possible regarding the eigenvalues and the eigenvectors. So now, the first thing that we need to do is that to find the eigenvalues, what we need to find the characteristic polynomial. So this is what we should immediately determine. And the characteristic polynomial, we get this from the
Determinant of a minus lambda I equal to 0.
A is equal to minus lambda I, this is equal to 0. And meanwhile, we might also, so this is one of the relationships we can make use of. Another one we can use is the following: lambda 1 plus lambda 2 plus lambda 3. What is this equal to? So we can say that this would be equal to the trace of A, and this trace of A is defined as the summation of the diagonal terms or diagonal numbers, which in this case, this would be equal to 3 minus 1 plus 0. This is equal to 2. Another relevant relationship which might help us to determine the eigenvalues is the following. The product of 3 eigenvalues will be equal to the determinant of A And regarding the determinant of A, we can try to do the expansion of the determinant using any rows or any columns. If we try to find a determinant here, it could be a good choice to pick up so we can use this one, okay, the third row. If we do it, we have the following, plus minus plus, so here we can have this one times the determinant of this 2 by 2 matrix, which is up here. This would be equal to minus 1 times 1, this is minus 1 minus 2 minus the determinant of, so we have this one, this is 3 plus 2. So this is equal, this is minus 3 minus, what is this, minus 5. This is equal to minus 8. Is this what we find for the product of these values, minus 8? Or is the determinant correct? Otherwise, we can find the following. This can be 3 times minus 1 plus 1. So if we do the expansion across the first row, 3 times minus 1, 0 minus 1, that's it, plus 1 times 0 minus 1, this is minus 1, minus 2 times 1 plus 1, 2. So this is equal to minus 3, minus 1. This means this, I think this is, yes, this is still minus 8. Okay, this is correct. So it looks like the determinant of this matrix is equal to minus 8. So we need to multiply all of the 3, 1, 1, minus 1, minus 2, 1, 0. Okay, so I have no mistake in here. And then let's try to obtain the characteristic polynomial. The characteristic polynomial would be the determinant of 3 minus lambda minus 1 minus 2, 1 minus 1 minus lambda. Here we have 1, 1, 1 minus lambda. So in this case, we would have the following. We would have 3 minus lambda times lambda squared plus lambda squared plus lambda, because we multiply this together, lambda squared plus lambda, minus 1, plus, because we do the expansion along the first row, we get here plus 1, that multiplies minus lambda minus 1, minus lambda minus 1, minus 2. So we're talking about this minus 2 times 1 plus lambda plus 1 times 1 plus 1 plus lambda plus 1 plus lambda. This should be equal to 0. So our polynomial, this is what it should be looking like. And then let's look at the terms. So the first term is minus lambda cubed plus lambda squared. And what are the terms that we can obtain for lambda squared? Here we have 3 is the multiplication of the lambda squared with this 3 minus 1. And then any other lambda squared, this is all, I believe. Then we get plus lambda times, here the lambda, we get it 3 plus 1. We get 3 because this is 3 lambda, multiplying these two numbers. And we have also this lambda as minus 1. This is 3 plus lambda. Any other lambda that comes up in here. We have minus 1 here. And minus 2, which is coming from this term in here. And now we have also plus lambda to the power 0. Lambda to the power 0 this will include the constant numbers. So the only constant here we have 3 times minus 1. We have here minus 3, minus 1, which is this minus 1 here. Then here we have 2 times minus 2 is minus 4. Minus 4, this is equal to 0. So we have a third order polynomial in lambda. So we have a P3 lambda. And this is what we were expecting actually. So we're expecting for P3 lambda to be equal to, as we can write this again, this is minus lambda cube. This is 2 plus 2 lambda squared. Then here we get 4 plus 1, right? Plus lambda. What is this? Can you help me here? 3 plus 1 is 4, minus 1, 3, minus 2, 1. Okay. Then here we have minus 8, minus 8. This 8, this is equal to 0. So here we have a polynomial of which we need to find the root. And in order to find the root in this type of polynomial, we can use a couple of tricks. These tricks might include trying to, so we need to factorize this one, okay? It might not always be very easy to factorize these. And one thing that we can use is, for the moment, let's multiply by minus 1, and we can obtain that we have here lambda cubed minus 2 lambda squared minus lambda plus 8. This is equal to 0. This is the same expression because we multiplied everything by minus 1 plus 4 lambda. Okay. So is everything all right, or is there need any?
With the
Yes.
equation, yes, but I don't think that it can be factorized so that we can find the roots. I think that we should use substitution.
Okay, let's see. Let's try to see, but let's solve the equations is all right first of all. And regarding this is 3 minus lambda minus 1 minus lambda. I'm just having a final look at the expression. Minus 0, okay. So the characteristic polynomial. So in order to find this, is that we can try to factor out this 8. This would be a good way to start with. So 8, it is divisible by 1, minus 1, 2, minus 2, 4, minus 4. So we can try to find what is the ratio between these lambdas, and we try to divide this one by lambda minus 1. Okay, this would be one choice. Because if 1 is a root, that means that this is divisible by lambda minus 1. And if we get no remainder, we can then try to factor out the second order polynomial. And yeah. Now, let's have a look, just to make sure for a moment. We can also try the following, which I can strongly suggest also you to use this. So you can use some software to try to determine the characteristic polynomials. So, ești conectat ecranul?
Yeah.
Okay, so let's try to write here the A. A is 3 minus 1 minus 2. Then we get 1 minus 1, 1, 1 minus 1, 1. And here we get 1, 1, 0, 1, 1, 0. So this is the matrix A that we started with. And what we can use here is we can try to determine a polynomial. And we can write here P is equal to poly A. And if we see that P is equal to poly A, we obtain these coefficients that we have also on the board. We get 1, which corresponds for lambda cubed, minus 2 lambda squared, minus lambda plus 8. Okay, this all is equal to 0. So it looks like the coefficients of the characteristic polynomial that we see here on the screen, they are the same as what we have determined. But now, so it looks like we are in at least we made no mistake so far. And let's try to let's try to see what could be a solution here. So if 1 is a root, then we have lambda cubed divided by lambda minus 1. We get here lambda squared. Here we get lambda cubed minus lambda squared, This is gone. Then we have, this becomes lambda cubed, this becomes minus, this is plus. So we have minus lambda squared, minus lambda squared minus lambda. Then this is equal to minus lambda. Then what is left is that we get, so it looks like this is not divisible by lambda minus 1. So actually 1 is, sorry, we can do it much easier. I made a mistake. So if we want to, not a mistake, I mean, we could try this way, but there is a shorter way, which is the following. If lambda is equal to any one of these numbers, then this identity should hold true for these values. So let's try for lambda equal to 1. If lambda is equal to 1, let's substitute it in this polynomial. So here we have 1 cubed minus 2 minus 1 plus 8 is equal to 0. This is not a root, okay? Let's see for minus 1, but it doesn't look very promising. Minus 1, to me, it doesn't look very correct also.
No, it's not.
It's not, right? Because we have minus 1, we have to beat up the minus 8, we cannot do it. Let's check for 2, if 2 is the solution. So 2 to the power 3, this is equal to 8. Minus 8, minus 2 plus 8, this is not equal to 0. So 2 is not a solution either. It looks like we're not going to have much luck with minus 2 either.
Try minus 1.6
Minus 1.6.
for lambda, yes.
Minus 1.6, which would be something like 8 over 5, right? Minus 8 over 5. Let's try that. Do we have much hope in that? Minus 1... Approximately. But, so let's try this one. You said that minus 8.6, then we can try minus 8 to the power 3 divided by 5 to the power 3 minus 2 times 8 squared over 5 squared minus 8 over 5 plus 8. This is equal to 0. So what we can do is multiply by 5 to the power 3 everywhere. So we multiply by 5 over 3, this is 5, this is 5 squared, and what we obtain is that we get minus 8 to the power 3 minus 2, 8 squared times 5 minus 8 times 25 plus 8, this is equal to 0. Is this 0? If we factor out the 8, we get 8 times minus 64, this is 2 times 8, minus 80, minus 25, no, it's not a root also, okay? So we don't have much luck also in here, but what we can try, let's see if we have an integer number solution. Let's try to find roots of P. Okay, it looks like we don't have integer number solutions. They look a little challenging for us. So, okay, we were not very lucky, but what we can follow here, it would be, we can have a look here. So, having the same, this is the matrix we are working on. P equal to poly A, this would give the coefficients of the polynomial, of the third order polynomial. This is lambda cubed, this is lambda squared, this is lambda to the power 1, and this is lambda to the power 0. So the roots of this polynomial, apparently we can obtain these 3 eigenvalues, where the first one, it is a complex number. The second one, it is the complex conjugate of the first one, okay? So you can see that the second one is purely the complex conjugate of the first, and the third eigenvalue, it is a real number. It is not a complex number, but it looks like we might not have much luck if we try to find the roots analytically, okay? So we can stop this here. I was hoping we can get some, I didn't have the solution of this one, but this beautiful program here can help us to stop before we waste too much time when we try to solve this one analytically. Okay, so we can have a look at a different example, which could be the full. We can pick up another matrix, but I need to let's remove this. It looks like what was worth regarding this example was that we just had a look at the, and by the way, actually, so the
Professor, I tried the value I gave you first, and approximately, yes, it is 0, the minus 1.6.
Yes, because what we saw here on Octave Online, that was true. It was a root. It is minus 0.62.
But I can predict that it must have 3 roots.
Yes, and as we check together, it looks like it has one root, which is a real root. Your entire screen.
The minus 1.6, right?
Yes. Ești conectat tot gradul? Ce ești conectat? So these are the eigenvalues that we see here. But one thing I was hoping was that the trace is equal to 2. So if we sum up all of these roots, so if we do sum of the answer, we really get equal to 2, which is the trace of the respected matrix, because we had the real parts, the complex parts, since they are complex conjugates of each other, they just cancel out each other completely. But then what we can try here is that, let's have roots is equal to here, then we can do answer 1 times answer 2. So if you multiply the first two numbers, this is what you observe. Then we have this answer, which is 4.9 times 1.62 and 0.6289. This is equal to somewhat around 8, or whatever that is. It should be minus 8. So we kind of prove. Ești кто vă prime ce am на ecran?
Yes.
Okay, so let's move on. We are presenting, stop
Professor,
presenting.
Eigenvalue, do you have to use just
Eigenvalues, I can write them on the board. So it looks like for this specific problem where the solution is not easily solvable using analytical approach, one of the eigenvalues is minus 1.62. So lambda 1 is minus 1.62. Lambda 2 is equal to the 1.8 plus 1.27. 1.8 plus 1.27i, and lambda 3 is 1.8 minus 1.27i. So lambda 3 is equal to the complex conjugate of lambda 2. And complex conjugate, we mean the following. So this is lambda 2 complex conjugate. So if any number a is equal to 3 plus 2i, then what is a complex conjugate? The a complex conjugate, it is 3 minus 2i. So if we just change the sign in front of the complex part of the number, we obtain what we call here, we can spell this completely, this would be the complex conjugate. And now, regarding this specific number complex conjugate, we need these numbers, I mean the complex numbers, because sometimes the solution of the characteristic polynomial, the solution is not always in real number space. Okay, so we say that any polynomial, if we have a polynomial, something like
Professor, I'm sorry for the interruption, but how did you find lambda 2 and 3? Because we found only one solution, 1.6.
we found using the software. We found it using the software.
So that means we have 3 solutions for the equation?
Yes. Okay. So you can use for any polynomial, you can, for example, you can come up with some, so what we showed here in the Octave Online, I was showing how you can obtain the characteristic polynomial of any matrix, and from the characteristic polynomial we find the roots. So what you can write down as in your notes is the following. You can define a matrix A, then the characteristic polynomial P, you can write that P is equal to the poly A, and then the eigenvalues would be written as the roots of P. Okay? So, кто di comanda po ti përdorni në Octave online, si që bëm pak më parë bashkë, e pa se si e bëm, po ti përdorni ose në Octave, you can use this in Octave, or in MATLAB programming languages. Okay? And the way to do it, I just demonstrated it to you. We can solve another system, but yeah, you can go over the recording and you can try to solve the same. So before a while, we showed that these were the three solutions. But now imagine that we have a polynomial here. How many solutions does this polynomial have? What could you say?
It depends on what domain. In the real numbers domain, only one. In general, three.
So I'm talking about this polynomial here.
Which? I thought you were talking about the previous
No,
example.
so this one. So this polynomial, this is a polynomial of 17th order in X, and this should have 17 roots, okay? But 17 roots, this does not always mean that they are in the real number domain, because we can have an equation which looks like this. We can have like x squared plus 9x plus 9. This is equal to 0. What is the root of this equation? Or the following, x squared plus 9 equal to 0. What are the roots of this equation?
-3. Oh. Okay.
So the roots of second order polynomial, they often are represented by the intersection of a specific graph with the x-axis, right? So this is x, this is y.
No solution.
So it has no solution?
Because the
Yes, it
square of
doesn't
a
have
number
solution
cannot be
because it
negative.
Yes.
doesn't.
So this is x squared plus 9. Because the y is equal to x squared, it would be this graph. So this would be y is equal to x squared, and y equal to x squared plus 9 would be much higher. So this means that x squared plus 9 has no root in the real number domain, but it has,
As
by
long as
definition,
it doesn't intersect the x-axis.
when it does not intersect with the x-axis, we find the solutions in the complex number domain. Okay. And the complex numbers is one type of expansion of the real number domain, because it includes also, because in this case, let me say it this way, so if you work for this specific case, this is x squared is equal to -9, and then x would be equal to the square root of -9. This is square root of -1 times 9. Square root of -1 is I. Square root of 9 is 3. Okay, so these would be the solutions. So here x1 would be 3i, and x2 is equal to -3i. So if we have a polynomial of the second order, we should definitely and always have two roots. Whether these two roots are in the real number domain, this is not an issue, but at least we can find them in the complex number domain. Okay, so in this case, the way to denote these two numbers, we can use a system which is very similar to the Cartesian coordinate system, where we can put here the real part of the numbers, and here we can denote the imaginary part of the numbers. So if you assume, I can write them down probably. So if you assume, for different numbers or complex numbers, we can have, for example, a complex number a. This can be written as 2 plus I. 2 plus I, it has 2 units here, and I, this is the complex number. So 2 plus I is this point right here. Another point b, which is 3I, is just here, 1, 2, 3. So this is the point b, this is the point a, and a number c, which is 2 minus I, this is minus I. Pra pjesën imagjinare e shkruajmë të boshti vertikal, pjesa reale të boshti horizontal. Okay? So, regarding these issues, I can offer you an example, and so that you can try to solve it, which is the following. Let's assume we have a polynomial in the power 16. Let's do it. X to the power 16 is equal to 1. So what polynomial is this? What order is this? This is P16 in X. And you need to find 16 different roots. So you have to come up with 16 different roots, but this one, we can have a look at this one in the next session. Any question for what we have so far on the board? If not, we can give another break.